Okay.
Okay. Hi, everyone. My name is Becky Lewis, and I'm a grad student here at the NSCL. Just a little bit about myself. The National Superconducting Cyclotron Laboratory. Thank you, Zach. Yeah, the National Superconducting Cyclotron Laboratory is here at Michigan State University. You can see at the bottom of my slides, in case you forget. But I'm a graduate student here. So just some background. I have a bachelor's degree in chemistry. I got it at Northeastern University in Boston. And I worked in the field of nuclear medicine for a few years before.
Excuse me, Ms. Lewis.
Yeah.
Are we okay? Okay?
Yeah.
Okay. I'm going to talk today about how we can save the world with radiation by focusing on careers in nuclear and radiochemistry. So you hear the word radiation a lot, but what does it really mean? When we talk about radiation, we're talking about something leaving the nucleus of an atom. And there are two main processes that this can happen. You can have an excited nucleus that has extra energy, and that can get rid of that energy as a packet or as a photon.
We're not seeing any PowerPoints.
Oh, no.
Okay. Let me. That's funny. What are you seeing? All right. Okay, there's Becky.
Hello.
She's real. All right, now let's do this whole thing. Share screen. Share it. Okay, and we can go back to slideshow. Okay.
How about now?
Is it seeing now?
Yes, thank you.
Woo!
Okay.
You want to hide this thing, otherwise we'll be looking at that the whole time.
Okay, so two processes that we can have this radiation leave. As I said, you can have this nucleus that has extra energy that can release that energy as a photon, or you can have just parts of the nucleus leave, like you can see here. So I just kind of want to remind everyone, in case we're all on the same page, what a nucleus is made up of. The nucleus is made up of protons and neutrons, and as I'm sure we've all learned, the number of protons is what determines what element is in the nucleus. So for example, here we have 6 protons. This is a carbon atom. And then in this case, we have 8 neutrons. So this is called a carbon-14. Now the number of neutrons just determines what's called an isotope. So one particular element can have multiple isotopes just depending on how many neutrons exist in that nucleus. There are a bunch of different types of radiation. I'm going to highlight 4 of them for you, just so you have an idea of what we're going to talk about later today, and just in general, it's kind of cool to know. So alpha radiation is known as alpha radiation because it was the first one discovered. And in this process, the nucleus loses what's known as an alpha particle. That's 2 neutrons and 2 protons. And what's left behind is a new nucleus of a new element and a new isotope. So everything changes in this type of reaction. Now, the second type of radiation is known as beta radiation. We're just moving alphabetically here. And in this case, a neutron will change to a proton and an electron inside the nucleus. And then that electron will be ejected out of the nucleus. In the next type, you have this gamma radiation. This is when you have that excited nucleus. It has the extra energy, and that energy is released as a photon. This is known as a gamma ray because of the type of radiation. And in this case, the nucleus doesn't change what it's like. It just changes how much energy is inside of it. And then finally, we have neutron emission, which, as you might guess, is really just where a neutron leaves the nucleus. So in this case, you have the same element, but a different isotope, because the number of neutrons has changed, but the number of protons has not changed. So we use radiation for a lot of things. The first 3 things that really come up is nuclear power. So you can see a power plant here. Nuclear medicine, you can see some imaging down at the bottom. And then what's known as radioactive dating. So you can actually determine how old something is by the ratio of a radioactive to non-radioactive set of nuclei. And these are the 3 main uses for radiation that people usually think of. But it turns out there's a lot of other things that we can use radiation for. Things like food irradiation, where our food is irradiated with gamma rays to kill off things like bugs and bacteria and to make shelf lives longer for our food. Fire detectors use radiation. There's an alpha source in our fire detectors, and that's what helps us determine if there's smoke. Clothing can be irradiated before it is treated with wrinkle-free or anti-stain chemicals, and that helps the chemical stick. Same thing is done for these non-stick cookware to make the chemical stick better so that you can use them for longer. Radiation is also used to clean up the outgassing from carbon power plants. You can see that they use here an electron beam that helps the reaction take place to remove dangerous chemicals before the gas is released into the environment. Glowing signs, I'm sure you've seen all over the place, like this exit sign I've shown here. Mostly in the past were made with radioactive materials to make them glow. A lot of companies have switched now to LED. It's a little bit cheaper, but a lot of the older signs you see, maybe even if you're in your school, if it's not brand new, are probably use some sort of small amount of radioactive material. And then even factories will use radioactive material to figure out and to standardize the thickness of their products. So in this case, this is a paper roller, and they're standardizing the thickness of their paper using a beta particle source, so those electrons that I showed you earlier. So there are a lot of uses for radiation, and a lot of people who need to work with radiation in order to get a lot of things done. So it is a very important thing to know about and to potentially work with. So you're probably thinking, so what? Someone does this work and it's very useful, but it doesn't really apply. Most people don't think it applies to them. Unfortunately, right now, there are not enough people going into many of these fields. So nuclear and radiochemistry are two of the STEM fields that have been indicated to need higher involvement from new students. This was done in a 2012 study that they called Assuring a Future US-Based Nuclear and Radiochemistry Expertise, where they made a very fancy name to try to make this seem very important, which it is. They looked into the current state of the field, where there are people employed, what fields need nuclear chemists and radiochemists, and kind of what it looks like in the future, if they're going to have enough people or if they're going to need more. What they really found, kind of a spoiler alert, is that they do need more students. There's not nearly enough people coming into the field to keep up with all the people who are currently leaving the field and retiring. So I've already thrown a lot of these terms out that you see at the top here, and I'm sure you've heard a lot of them in the news, but not everyone knows really what they mean and how they're different. So the field itself started with radiochemistry. This was when people or researchers like Marie Curie used chemical techniques to discover information about radioactivity. This is still the term that's used when chemistry is being done on radioactive material. And so there's huge fields of radiochemistry where there's still active research to be done. Now the term nuclear science describes just the broad study of anything that has to do with the nucleus. So this could be chemistry, this could be physics, engineering, math, and it keeps going. Biology still is part of nuclear science. So this is what people call the safe term to use when describing nuclear studies, because it kind of covers everything and everyone can be under that umbrella. Now nuclear chemistry, which is technically where I am, is very closely aligned with nuclear physics. So usually the only difference is a background in chemistry or physics. So here at the NSCL at Michigan State, we nuclear chemists work with the nuclear physicists on the exact same problems. And the only difference really with us is that I will have a degree in chemistry and another person will have a degree in physics. But it really doesn't affect the work that's being done. This is not that surprising. A lot of fields are moving in this direction, where there's kind of fuzzy lines between what you studied and what you work with. And it helps really build these collaborative efforts to help people solve problems that they might not have been able to solve before. So that 2012 study that I talked about identified 5 areas that need more involvement from nuclear chemists and radiochemists. These were basic research and education, medicine, energy and power generation, national security, and environmental management. So I'm going to go through each one of these and kind of talk about what's in them, what they mean, and maybe what type of work can be done in them for chemists especially. So basic research and education is normally done at universities. That's where the majority of this is funded and happens. I have here this nice bar graph that I found. This shows for a number of academic years the number of advisors and the number of theses that were in nuclear and radiochemistry fields. So advisors is shown in these little red bars here. An advisor is someone who helps or oversees a graduate student who's getting their PhD. So it's you usually have less advisors than you do graduate students. One advisor can oversee more than one graduate student. But you can see here that the number of advisors and the number of graduate students is very small in general. Less than 25 advisors and less than 35 theses being completed, even in the most recent year that they have here, which is the highest number. It's not a lot. This is the entire US. It's not a lot of people who are getting degrees in this and who are working in this field at universities. And remember, universities is where all this basic research is happening. So we need people who are in the field at these universities doing this work. You can see there is sort of an increase. It's very small, and the scale is pretty small, so it's not much of an increase. But unfortunately, it's not nearly enough of an increase to keep up with the demand for people who are trained in this field, and also for the spots that are opening for people who are retiring in this field. There's a big group of people who have been leaving the last couple years because they started when nuclear science started in the 40s and 50s, and now they're leaving, and so we need a lot of new people to come in. Now, there are many facilities across the US where this basic research is happening. There are big ones, like here at Michigan State, where we have the NSCL and the upcoming FRIB, which is the facility for rare isotope beams. We're pretty much expanding our capability here so that we can move from the research we do now to just bigger and better research with FRIB. We're unusual, though. There are very few universities that have a large-scale facility like this. Most universities are much smaller, and they have much fewer people around and much smaller laboratories, and their research is normally done at other universities like ours or at national laboratories. I've highlighted some of the national laboratories down here that do a lot of this kind of research with students. And it's interesting because even being here at a big facility where we get to do our research right in our backyard, pretty much down the hall, we are not restricted just to doing research here. So it's a nice capability, but it's still, I still could do an experiment if I wanted to at one of these national laboratories or even at an international laboratory in Canada or Japan, because this field is very collaborative. So a lot of people will work on big experiments and travel around the world even to work on this science. That's pretty exciting. A lot of fields are like that. The nuclear field is very like that. So there's a lot of collaboration and a lot of sharing of facilities and science, which is pretty exciting. So going more into the industry side of things, I want to look at nuclear medicine for a little bit. I know this is my field for a little while, so this is something that I know maybe a little bit more about and also have just more experience, but it is really interesting. And I'm going to focus on the two parts of nuclear medicine. There's the diagnostic side and the therapeutic side. So the diagnostic side uses gamma rays, which I showed you before are emitted from that excited nucleus, and they are using gamma rays that originate from within the body. So in order to get a gamma ray that starts from within the body, you have to put it there somehow. So in this case, the radioactive material will be introduced on a molecule that will travel to somewhere inside the body. Now the molecule is picked because we know that it will go to the part of the body that we want to study. And usually this is tumors. So we'll pick a molecule that is known to travel to tumors, and then we will follow that tumor where the tumor exists by looking at the radiation that is emitted from that area. You can see here on the left, we have a guy getting his brain scanned, and there must be a tumor there. So the molecule has gone there, the radiation is coming out and is being detected by what is called a gamma camera in this case. And then using that detection, they can reconstruct a scan of the brain, and they can see where they have a high concentration of that molecule or a low concentration of that molecule. On the bottom, we see another person with a full body scan. Unfortunately, this person has a lot of tumors, and but you can see that that high concentration in red there shows where that particular molecule is most abundant, and so those are where the tumors are. So this is very useful. You don't have to cut anyone open in order to do this, to find all these tumors, and then it makes treatment easier in a sense that you know what you're getting yourself into before you really start treatment. These instruments look like the one down on the bottom right. You can see you slide the person right into the center of the detector so that you can try to catch as many of the gamma rays as possible and get the best reconstruction that you can. So the other side, as I mentioned, is the therapeutic medicine. This is when radioactive material is introduced into the body to intentionally cause damage. The idea behind this is usually, again, with tumors, you're trying to destroy that tumor. And so you want to send the radiation into the body so that it can target the tumor. There are two ways of doing this. You can have external radiation that passes through the body. That's shown on the right here with what this is called a gamma knife, where they direct the gamma radiation directly at the tumor, where it can kill it off without doing, well, hopefully doing minimal damage to all of the other cells in the brain. And then you have internal radiation, where you will attach or encase a radioactive nucleus to a molecule that will bring it to the tumor, and then it will directly pretty much bombard that tumor with radiation. So in this case, this is a gold sphere that is encasing an alpha source. So in the middle here you have radioactive material, and as it decays, the little alpha is able to escape, and then that will target the tumor and kill it off in just that one area instead of being a whole body dose. And you're able to make more use of that radiation and also limit the exposure to the person. These gold spheres are kind of a new development for this alpha radiation. And as I've shown here, there's many different illnesses that can be treated by therapeutic nuclear medicine. This is a pretty big field, and there's a lot of money in it because there's always a lot of money in medicine. But it's important to limit the exposure that you give people when you're doing therapy. And so stuff like the gold spheres are important developments because we can really target what we want to and reduce the exposure in other areas. So in nuclear medicine, there are many things for a chemist to do. The first step really is producing that radioactive isotope. You usually want to put into someone's body something that does not last very long because you don't want a lot of radiation hanging around inside their body for a long time. Because these are so short-lived, they usually need to be produced on-site. A lot of times these are done in hospitals. And so you can produce that isotope and put it on the molecule and use it right away, and you don't have to try to ship it in from somewhere else. There also needs to be making all of these molecules. You don't just get a molecule that has a radioactive atom on it. You have to usually even just make the precursor, the first step, and synthesize the entire process, and then add the radioactive molecule at the end, which is called labeling. And you can see at the bottom here, I've actually shown some of the work that I've done in the past, where we labeled with this fluorine-18. This has a half-life of about 2 hours, so it's really nice for imaging and for doing diagnostics because it's enough time to add it to a molecule, get it to the patient, get it inside the patient, and then still look at the decay. And you can see that we use something called microfluidics, which is where you actually flow all of your different parts of your reaction together. This is nice for radioactivity because you're not actually touching any part of the reaction. It can be done behind closed doors, pretty much. But there is a lot of hand labeling that's done, where people will mix things and add things by hand. And it is a delicate process, and these things are short-lived. And so development of methods to do this type of labeling, to do this type of chemistry are very important, both for the safety of the patient and for the safety of the researchers. Now, the next one that I want to talk about is this energy and power generation. Again, this is pretty much nuclear power plants, but there's a lot of different processes that need to be monitored during the evolution of nuclear power. From the very beginning, such as knowing where your radioactivity is going to be in the reactor, to then knowing how it will act inside the reactor, to then knowing when it's done being inside the reactor and when you need to pull it. You need to be able to understand how to safely dispose of it and how to monitor the environment and the stored radioactive material to make sure it's not leaking into the environment. So there's a lot of processes that a chemist needs to be involved in to make sure that all of this is safe, especially because radioactive material, just because it was radioactive, it doesn't mean it doesn't react with other molecules. So reactions will happen that a lot of times people from other fields will not think about, and so you need a chemist there to make sure that nothing bad is happening. The bottom left here, or bottom right, I've shown kind of a simple schematic of what's known as a boiling water reactor. So I hope it's moving on your side. It should be. Yeah, okay. And what you can see here is on the left is the reactor vessel, and inside of that are the control rods, which is the fuel rods and the control rods. You have radioactive material in the fuel rods and control rods to stop anything that happens if it's not going so well. And what happens is during the process of radioactive decay, if you remember, I showed you that you lose energy when you have that excited nucleus, and that energy can be used to heat water. So the water is heated, it turns into steam, and then the steam is used to turn that turbine, which can then generate the power. So this is a very simple nuclear power diagram, but this is actually how a lot of them work. Boiling water reactors are relatively common in the field, and they're able to kind of just make the power that we need pretty safely as long as everything is monitored. So another huge aspect is national security. So we have a nuclear weapons program in the United States, and the maintenance of that program is known as stockpile stewardship. So the idea behind that is we have weapons. They were produced mostly in the 50s and 60s, and they're getting old. We need to maintain these weapons and predict how they would be affected by their time sitting around, but we can't actually test any of them because that is no longer allowed. So a lot of times we will utilize simulations to predict how a weapon will act and how it might degrade over time. Unfortunately, simulations are only as good as the data you put into them. So we also need to do experiments on all the different parts, so on the electronics, on the casings, on the material inside. Everything needs to have some sort of experiment done on it in different parts so that the data that's going into the simulations will be good, and we'll get good predictions of what we can expect. We also have a non-proliferation and arms control part of our national security that is very, very large. So as I'm sure a lot of you have been hearing about the Iran agreement, we do have multiple international agreements to prevent the use of nuclear weapons. This is probably the most recent and maybe the most heavily argued in a long time. This was a really big one. But just having an agreement doesn't really mean anything if you can't verify that people are following that agreement. So verification is a really big deal, and a lot of that comes down to testing for illicit nuclear material, if it's being moved through Europe, if it's being moved into the United States or through the United States. A lot of times there's a lot of testing done at ports because people will try to sneak nuclear material in shipping containers, and so they built remote sensing systems like the one I've shown on the bottom in the middle, where this truck is driving a shipping container through a remote sensor, and they're going to look for radioactivity in that container before the truck is allowed to leave. So a lot of these arms control measures are still being developed because it's hard to do this type of remote sensing, and a lot of these international agreements do not allow for direct testing of weapons and nuclear materials. You need to be able to do this indirect testing. Also, at the same time, you need to be able to respond if there is a nuclear event. This is one of those contingency plans that everyone hopes will never ever have to use, but is there as an option and needs to be ready to go at any point. The big concerns are what type of material was used, what kind of effect it will have, what kind of people will be affected, how widespread the effect is. There's a lot of issues that need to be dealt with, and all of those procedures need to be established before this happens. So there's a lot of research done on how to figure all of these answers out as quickly as possible. The last one I want to focus on is environmental management. So there are a number of current and former nuclear sites that we need to either be monitoring or actually clean up. On the bottom left here, I've shown a map that has a small number of the current what are known as nuclear waste sites in the United States. The ones that are currently operating is the Oak Ridge Reservation, the Savannah River Site, the Waste Isolation Pilot Plant, known as WIPP, which is by Los Alamos National Lab, which is also still operating, and the Idaho National Lab. And then there are two closed test sites, which is the Nevada test site where they used to test nuclear weapons, and the Hanford site, which was a site for making nuclear weapons and nuclear power. And then the Yucca Mountain Repository, which was proposed to store a lot of nuclear waste, but never actually got there. They've never put anything inside of that. Of these, the Hanford site is our biggest issue. The Hanford site was operated in the 50s and 60s, a little bit later, and when it closed, their containment vessels breached. So they actually did not do their containment correctly, and they're having a serious environmental contamination issue, where you can see on the right kind of a cartoon of where this contamination might be going and how it can spread into the water table. So they've had a lot of work is being done over by the Hanford site to monitor the environment, to see where the radioactivity is going, to figure out how to get it out of the environment, to clean it out of the sands and the soil and the water, and how to recontain these vessels because they're buried underground. And so that's a pretty difficult process to try to go through. So the big area of research is in separations chemistry. The idea behind this is that it's very, very expensive to store radioactive material. There's a lot of steps you have to go through, and a lot of money needs to be spent on inspections and safety. And so you want to try to minimize the amount of material that is radioactive. The best way to do that is to remove everything you can that's radioactive, and then you can dispose of that in the appropriate manner, and then everything else you separated it from can be thrown away as you normally would. So separations chemistry is just different processes for separating out the radioactive material. A lot of research is being done small scale to try to test different filters and different chemicals and try to see the best way to do this. But then the next step would be to scale it up. So that's the next part of the research, is to try to scale up the best sets of separations and use them in any radioactive site that is currently running. There's also the development of new storage techniques. We don't want what happened at Hanford to happen anywhere else, so they need to build better storage tanks if they're going to dispose of liquid radioactive material, of which there is a lot. So I showed you that boiling water reactor before. That actually flows water directly through the reactor vessel. And so all of that water is now considered radioactive because it is in contact with the radioactive material, and probably some of it dissolves into the water. And so if it's not possible to remove radioactive material from that water, all of that water needs to be disposed of as radioactive material. So you need these big tanks, but you have to be able to prevent the water from leaking out. Another way that they're starting to dispose of radioactive material is through the process of vitrification, which is turning it into a glass. So they try to separate out first as much of the radioactive material as possible, and then they form a glass with that radioactive material. So the whole glass is radioactive, and that whole thing needs to be stored as such, but because it's a solid, it's much less likely to leak into the environment. However, it's not impossible for it to leak in some way if it undergoes a chemical reaction, and so a lot of research is being done on how the glass will react with real environmental conditions so that we can store it appropriately and it won't contaminate the environment. So if you do want to go into nuclear radiochemistry, there are a lot of educational opportunities. You don't have to go to an undergraduate university that has these types of programs. There are a few out there, but they're not really, really common. And so a good way, the way that I got started in this field, is to do something like a nuclear chemistry summer school. The American Chemical Society and the Department of Energy fund a summer school every year at the San Jose State University and Brookhaven National Lab. And so you can go there. It's a 6-week course. You can learn all about the field, and you can do some sort, like a little bit of research. It's more class-based, but there's labs, and you can kind of learn how all of this works. There's also a nuclear forensic undergraduate summer school if you're more interested in nuclear forensics, which is more along the lines of figuring out what has happened if there's nuclear material somewhere. That travels around the country. That's been held in Las Vegas, a couple places in California. It's been held, I think, at Florida as well. So there's a lot. I'm not so sure about that. There's a lot of places that one travels to, and that's pretty interesting. There are also summer internship programs. Usually you get paid for these, which is pretty exciting. The big one is the Glenn T. Seaborg Institute summer program. That's at Lawrence Livermore National Lab in California. And then if you do decide to go into graduate school in this field, there are a number of graduate fellowships to take advantage of that will help you do research in this. And in graduate school or in undergrad, you can do summer opportunities at national labs. I actually have a picture here. I worked at Oak Ridge National Laboratory for a semester when I was an undergraduate, and this is one of the labs that I worked in with the glove boxes. So these were plutonium and technetium glove boxes, which is pretty exciting. So if you get a chance to do some hands-on research, you can really test out the science and see if you like it, and usually get paid for it too, which is great. So I do want to make one final note on radiation. This is probably my favorite picture about radiation. You can see that big box. This is the minimum annual radiation exposure linked to the increased lifetime risk of cancer. So that's not a number that's easy to calculate. But a lot of work has been put into trying to figure out how dangerous radiation is and how much of a dose you need to get before you really need to be worried. And this was set at 10,000 millirem, which is a unit of exposure. You can see that getting just a CT scan, which is X-rays, is much smaller than that. Flying round trip from New York City to LA, a transcontinental flight, that's only 5 millirem, so that's nothing. You could do that 100 times a year, you'd be okay. Getting an X-ray is only 10. Just annual exposure from food and water, because there are naturally occurring radioisotopes everywhere, is only 30 millirem. So in the end, radiation is not something that we normally need to be worried about. And working in a radiation facility, there are so many safeguards that your annual exposure is very small. And so when people say they're worried about how much radiation there is and it's going to give them cancer, you can look at something on this scale and say you really don't need to worry unless you're trying to get a CT scan 10 times a year, which I don't think they'll let you do anyway. So should be okay. So thank you very much for listening. If you have any questions, I put my email here in case you want to ask anything besides after this chat. And a picture of my group, we went to the FRAB construction site. And so that's what it looks like right now. But it's going to get better. We're going to do some great science there. So thank you very much.
Questions? You might have Ms. Lewis? Oh, I think she probably stand up.
Hi there. Going back to like the medical diagnosis stuff, when you're doing the gold casing around the alpha particle, how do you construct something like that on such a small scale?
It's hard. They use a film technique where they take these tiny particles and they kind of diffuse the radioactive material into a shell. So they've already formed these small shells through a chemical reaction. And they can diffuse the radioactive material in, and then they can start dumping these spheres into the different layers until they've layered all the way up to the gold. And then the molecules that go on the outside.
Right.
Why did you want to study nuclear chemistry?
So I went into undergraduate as a chemistry major because I love chemistry. And I started just doing chemistry and not really knowing where I wanted to go with it. But as I mentioned, I worked at Oak Ridge National Laboratory, and I actually got that position kind of by accident. I applied to what's known as the Student Undergraduate Laboratory Internship, which allows undergraduates to work at national laboratories. And the woman who picked me was a nuclear engineer, and I started doing some of this chemistry and working with this radioactive material, and I realized it was really interesting. So because of that, I went into nuclear medicine. In Boston, there's not much to do with nuclear radioactivity besides nuclear medicine. So I did some of that for a few years, and I went to the summer school that I mentioned, and then I finally ended up here.
Got one coming in from the
question.
ether.
Oh.
What do you want to do after you graduate?
After I graduate, I would really like to work at a national lab. So I've already done it for a little bit of time, and I really liked how it worked. The work I'm doing here is in beta decay studies. So I'm looking at beta decay and what happens to the nucleus afterwards. That's very interesting. I really like working with the big collaborations and the big detectors and kind of the bigger science like that, where you need a lot of funding. The national labs are a good place to be. I think that would be really interesting, and I want to continue on in nuclear chemistry and nuclear physics.
You mentioned programs for education for young people. Are those for high school students as well?
There are very few high school programs for nuclear chemistry. There are for undergraduates. They're out there, but I don't know as much about them. I didn't do any, and I don't know. And there's more for physics. I think Zach knows some more for physics.
One for nuclear astrophysics. It's Pan, and Bill can tell you more about that.
Yeah, unfortunately, because nuclear chemistry is so much smaller, it's harder to get those programs going earlier.
How are radioactive materials separated at their wastes?
By their chemistry. So a radioactive atom will act just the same as its non-radioactive sibling. So again, as we know, the proton number is what determines the element, and it also determines the electronic structure, so the electrons around the nucleus. And so the same element with different radioactive isotopes or non-radioactive isotopes will act the same chemically. And so you can utilize that chemistry to separate out everything of the same element, which means you will get non-radioactive isotopes if you have them that will separate out at the same time. But the concern is mostly getting like radioactive lanthanides or actinides out of water, and you're going to do a pretty good job.
Hello. What type of jobs specifically in the field of medicine would students be possibly going to school for in this kind of field of radiochemistry?
So chemistry is a good one. If you do like chemistry and you want to be on that side of the research or even the production of these molecules, it's really useful to have that background in chemistry. Medical physics is actually its own field, and you can get a degree in medical physics, and that's the same idea where you're not making the molecules, but you're using them. And you're usually looking at the scans and helping the doctors that are doing the therapy. And you can be a doctor. You can be a doctor who does nuclear medical therapy and treats cancers that way. And even radiopharmaceuticals are their own fields. You can go into pharmacy and learn how to utilize these radiopharmaceuticals. So there's a lot of different ways you can go. Science in general is pretty safe.
Excellent. Go for it.
So if you're going to go into like geology, that's where I started. Yeah, would you have to have that kind of background for like carbon dating?
No. I know a lot of people who are in geology like to get into that environmental stuff to do carbon dating. Carbon dating now has gotten to the point where the research is in more mass spec, which is more of a chemistry thing. They're trying to get even more accurate and even just smaller concentrations of isotopes. And so a lot more chemists are getting involved in that kind of thing.
You mentioned a number of applications for radiation. You mentioned a number of You mentioned a number of different applications for radiation, including like medical research, nuclear power generation, nuclear weapons, and the like. What role does the work at NSCL at Michigan State play in that research?
So a lot of it is more basic research. The applications are not there's not always a direct link between what we do here and a nuclear power plant. But we are understanding what the nucleus looks like and how it acts, and making it easier to predict how these radioactive materials and isotopes might act in the real world. But the direct link, we don't really do research here that is going to help us make a new fuel cycle to put right in. But we're understanding how things work so that we can predict what we can do with them.
Okay, so you've kind of talked about it already, but I'm just curious. You talked about like the undergraduate program. How long exactly does it take to like get a degree in either like nuclear chemistry or nuclear physics?
So it's usually the 4 years that you would expect. If you do summer programs to get kind of your experience, if that's what you want, it should only take the 4 years. I went to a university that does what is known as a co-op program. You take 6 months off at a time and you work, and that's how I got the time to go to Oak Ridge and do some research there. And normally that type of program takes more like 5 years because you're taking a break from your classes to try to get this experience. But just going into nuclear chemistry or nuclear physics as an undergraduate doesn't mean you're going to take more time. As a graduate student, you're still looking at about 5 years, which is normal for graduate school. Here at the NSCL, we move pretty fast, actually. People will get out sometimes in 4 or 5 years, which is exciting. And it kind of just depends on timing and when you can run experiments and the work that's being done. But just being in nuclear doesn't really extend the amount of time you spend in school.
What kinds of things do they think they could do right now to get into an awesome career like yours?
Well, to do right now, you need to figure out how much you like science. If you don't like science and just doing research and thinking about crumbs like that, it's tough to do this kind of work because, especially in graduate school, that's the whole point. You're trying to solve problems that people have never solved before. Also, if there's anywhere around that will let you follow them or even try out some of this kind of research. I don't know what types of nuclear facilities are around near you, but if there's a reactor or there's a university that will let you come in and learn about it, the more information you have when you apply to programs that shows those people that you're interested in, that you thought about it, the better your chances are of really getting a good spot and then learning as much as you can.
How do you evaluate the danger associated with an isotope?
The dangerous, I'm sorry? What?
Is an isotope with a short half-life or a long half-life more dangerous?
It depends. So a shorter half-life is immediately considered more dangerous in a sense because it's releasing more radiation right away. But what it really comes down to is how much there is in front of you. So if you have just a tiny bit with a short half-life versus a whole lot with a long half-life, you're looking at almost the same amount if you get the right values together. The good thing about things with short half-lives is you put them in, you let them decay, and you come back and you're fine. The radioactivity is pretty much gone. So in that sense, it's safer, but in the immediate effect, you're getting a lot more radiation at once.
How are waste products handled at NSCL?
I'm not too sure. So a lot of our things are very short-lived, and they decay away, so we don't have to worry about most of them. I don't know if anything really long-lived that we... Yeah, Zach says no problem. So yeah, I mean the things we make here are very short-lived, and that's why we're here. We make these things that most people can't make, and they are very short-lived because they're not normal nuclei, and so we're able to just let them decay away, and then we're good to go.
Anyone have any more questions? Otherwise, we're closing in here, and I certainly would want to thank Ms. Lewis here for a wonderful presentation.
Thanks for listening in.
Thank you. Thank you.